Have you ever wondered if artificial intelligence could learn to reason and think more like us? Today, I'm excited to share a fascinating development called PRefLexOR, which stands for Preference-Based Recursive Language Modeling for Exploratory Optimization of Reasoning. It's a new framework that aims to enhance AI models' reasoning capabilities by allowing them to teach themselves through iterative refinement, much like how we humans learn. Traditional AI models often have limitations in how they process information. They typically take input and produce output in a single pass, without revisiting or improving their thought processes. This can limit their ability to handle complex reasoning tasks or adapt to new challenges. PRefLexOR changes the game by introducing recursive reasoning and preference optimization. Let me break that down. Recursive reasoning means the model can revisit and refine its reasoning steps. It's like when you're solving a complex problem. You might try an initial solution, reflect on it, realize it could be better, and adjust your approach before arriving at a final answer. Preference optimization, on the other hand, guides the AI model to prefer better solutions over less effective ones. Think of it as teaching a student not just to find any answer, but to find the best possible answer by learning from feedback. An essential component of PRefLexOR is that it draws inspiration from reinforcement learning. If you're not familiar, reinforcement learning is a type of machine learning where an agent learns by interacting with its environment and receiving feedback in the form of rewards or penalties. In PRefLexOR, the model uses this concept to iteratively improve its reasoning based on feedback from previous attempts. Now, how does PRefLexOR actually implement this? It uses special thinking tokens to structure the model's reasoning process. These tokens act like markers, indicating when the model is processing different parts of the problem. This structured approach creates iterative feedback loops, allowing the model to refine its reasoning over multiple cycles. Let's delve into the 3 key phases of PRefLexOR that make this possible. Phase 1 is called Structured Thought Integration Training. In this phase, the model is trained to process the new reasoning tokens, guiding it to structure its reasoning explicitly. Preference optimization, during this phase, ensures that the model learns to prefer well-reasoned, step-by-step thought processes. In Phase 2, Independent Reasoning Development, PRefLexOR takes things a step further. Here, the reasoning tokens introduced earlier are masked, challenging the model to develop its own internal logic without explicit guidance. This phase introduces more difficult tasks, pushing the model to reason autonomously, thus enhancing its flexibility and ability to tackle ambiguous problems. Phase 3 is the recursive reasoning algorithm, which comes into play during inference, the stage where the model is actually generating answers to new questions. In this phase, PRefLexOR engages in recursive reasoning cycles. The model revisits and refines its responses, continuously learning and improving its decision-making based on feedback loops. This recursive structure ensures that the model can handle increasingly complex, cross-domain challenges with greater depth and coherence. An exciting aspect of PRefLexOR is that it's effective even in small language models, those with only about 3 billion parameters. Despite their size, these models can iteratively teach themselves to reason with greater depth and clarity. It's like seeing a novice learner rapidly improve through dedicated practice and self-reflection. To illustrate how PRefLexOR can integrate knowledge across different areas, let's draw an analogy with Hermann Hesse's novel, The Glass Bead Game. In the book, the glass bead game symbolizes a synthesis of all arts and sciences, a way of connecting ideas across disciplines to gain deeper understanding. Similarly, PRefLexOR enables AI models to integrate knowledge from various domains, improving their reasoning by making connections that might not be immediately obvious. The researchers demonstrated PRefLexOR's capabilities in the field of biological materials science. They tackled complex, cross-disciplinary problems, showing that the model could handle tasks both within the domain and in cross-domain applications. This highlights the model's flexibility and its potential for broader applications. They also explored various reasoning strategies, including thinking and reflection modalities. By constructing a multi-agent recursive self-improving model, they showed that responses could be successively improved through repeated sampling during inference. In simpler terms, the model doesn't just provide an answer. It thinks through the problem, reflects on its reasoning, and refines its answer. So why is all of this significant? PRefLexOR represents a meaningful advancement towards AI systems that can reason more like humans. By enabling models to self-teach and adapt through recursive reasoning and preference optimization, we're opening the door to AI that can handle complex tasks with greater intelligence and flexibility. This approach could have far-reaching implications across various fields, not just in science, but in any area that requires deep reasoning and adaptability. Imagine AI systems that can independently tackle new challenges, continuously improving their understanding and performance. In conclusion, PRefLexOR is an innovative framework that enhances the reasoning capabilities of AI models by combining preference optimization with recursive reasoning inspired by reinforcement learning. It allows models to self-teach, adapt, and improve their cognitive abilities autonomously, even in small-scale implementations. It's exciting to see how this method mirrors natural learning processes and brings us closer to developing AI systems that can think and reason in more sophisticated ways. The potential impact on science, engineering, and beyond is truly remarkable.